We are in the lab today and we're going to talk to you about our continuous wave radio frequency EPR spectrometer, about how it works and how we put it together from instruments and components here on the bench. Now I say we because I'm not on my own today. This project is part of Professor Edward Laird's research group here at Lancaster University, and I'm going to be joined by most of the researchers on the project and a couple of our skilled Lancaster technicians to show you how it's built and to give you a demo. Now, for those of you who have clicked on a video of how to build an EPR spectrometer because you want to know how to build one, I'm guessing that you know a little bit about the theory already. But for those of you who are just curious, let me explain a little bit about what we're actually doing here. Hopefully that'll help. So EPR stands for electron paramagnetic resonance, and it's so called because electrons have a magnetic dipole due to their quantum property of spin, and we can exploit that using an EPR spectrometer in order to get a resonance effect. So let me explain what that means. As you might know from quantum mechanics, an electron can either be spin up or spin down in any particular orientation, and there isn't usually an energy difference between those two levels. However, if you take the electron and you put it in a magnetic field, that causes there to be a difference between spin up and spin down in the axis of the magnetic field, and that's called the Zeeman effect. And the reason for it is that it takes less energy for the electron to be aligned parallel to the magnetic field than it does for it to be aligned anti-parallel to the magnetic field. Now, in EPR spectroscopy, we can exploit that energy gap. And what we do is we get a sample containing atoms which contain unpaired electrons in a particular atomic orbital. And we cause those electrons to transition from the lower energy state to the higher energy state, and back again. And the way we do that is we put the sample in an oscillating magnetic field driven by an electromagnetic wave whose frequency corresponds to the amount of energy required to cause the transition. And that whole thing sits inside the static magnetic field. And when we get the value of the field and the frequency of the signal correct, the electrons transition. And we call that transition a resonance. And when we do that for multiple values of field and multiple frequencies of driving signal, we get an EPR spectrum for the atom. Hence, finally, we have electron paramagnetic resonance spectroscopy, EPR. Now, we've covered a lot of ground there in a very short space of time, but we do intend to do another video, focus more on the theory, and in particular the very exciting endohedral fullerene that we're using for this experiment. But for this video, we really focused on the build and how it works. So let's start that with the circuit diagram. So starting on the right hand side of the diagram, you'll see we've got a DC supply connected to two inductors. Now that is a Helmholtz coil setup, and that's how we generate our static magnetic field, which is the one that we sweep for the experiment, and produces the Zeeman effect in the sample, and that is B0 as it is labelled on the diagram. Moving to the centre of the diagram, we have our RF signal generator, and that produces a radio frequency signal. The reason we're using radio frequency is because the molecule that we're experimenting on has a clock transition at around 38.6 megahertz, and the stimulation of that transition is the primary motivation for this experiment. So our RF signal generator outputs a signal into a splitter, and that goes into two directions. So following the right hand path, we have a variable attenuator. We can adjust that so that we don't overdrive the sample. The signal then passes through into a directional coupler, which sends the signal up this coaxial cable and into our coupling loop. That is just a single loop of wire shorted so that the centre of the coaxial cable is connected directly to the ground. That is then in turn inductively coupled to our electrical resonator, which sits around our sample tube, which in our case is a vacuum tube inserted into the apparatus containing solution, which contains our sample. And this electrical resonator, which we'll show you a little bit more of later, is essentially an RLC circuit with resonant frequency f equals 1 over 2 pi root LC. Now the reflected portion of the signal comes back down our signal coaxial through the directional coupler and into our filter and amplifier chain and into our mixer. Now as you can see, the mixer receives a signal from the RF signal generator also, and what this does essentially is multiply those two signals together. Now because of the way that the sines and cosines fall out of that calculation, that produces a DC signal proportional to the reflected component of the signal from our coupling loop, which is output into another low-pass filter before being passed to the input on our lock-in amplifier. So moving up here to the top centre of the diagram, we have a waveform generator. Now this too outputs in two different directions. Let's follow the right-hand path. That is passed to our modulation coils here in the apparatus on the right. Now the effect of these modulation coils is to modulate the static field generated by our DC supply and Helmholtz coil setup. And the reason we do that will become clear shortly when Ed talks to you about the lock-in amplifier and how it works. And that produces the magnetic field B mod, oscillating magnetic field there. As you can see, B1 is the oscillating magnetic field produced by our electrical resonator coupled to our coupling loop driven by the driving signal from the RF signal generator. The other output from our waveform generator is passed to the lock-in amplifier, which uses that to demodulate the signal from the mixer. So the output from the mixer in fact isn't a true DC signal. It's a DC signal encapsulated in our modulation frequency, which for us is around 6 kHz. The lock-in amplifier demodulates that and produces our signal graph. Okay, we'll show you a demo of that shortly, but first let's have a look at the equipment in real life. So here is our instrument stack. Do excuse the scrappy piece of foam there. It's actually a high-tech vibration damping mechanism. On the left there we've got a static DC power supply. That is just to power the amplifiers. Underneath that we've got a Zurich Instruments MFLI lock-in amplifier. On the right, the large green display, that's our DC power supply, remote controlled to adjust the Helmholtz coil setup. Our signal generator just below the DC supply. And finally on the bottom there is our waveform generator, which drives our modulation coils. And lurking just at the back there we have our variable attenuator. So this is our filter and amplifier chain. You can see just on the left hand side there's a DC block. I didn't mention that on the circuit diagram, but we found that helps to further reduce noise in the system. So just to the right of the DC block is the directional coupler, followed, moving rightwards, a high pass and low pass filter, two amplifiers, a further high pass filter and the mixer on the right. And finally we have another low pass filter on its way into the lock-in. So here is the apparatus itself. You can see the large coils there are our Helmholtz coil setup, connected to the DC supply via connectors on the right. The vacuum tube there, you can see, is inserted into a cage in the centre of the apparatus, and everything is suspended from an aluminium frame. Moving down there, we see the central cage, which contains our modulation coils and sample, and at the bottom here we have an adjustable differential screw which we made here at the university, which is what moves the coupling loop up and down in order to critically couple the resonator. So if we open up this central cage, which is an aluminium box, we can see that we have our modulation coils in there and the platform which supports the movement of the coupling loop with respect to the resonator. And we have modulation coils set on the top and bottom and on the sides so that we can run this apparatus in parallel or perpendicular mode with respect to the main magnetic field B0. Now fortunately we can show you what goes on inside the spectrometer in a bit more detail than usual because Eve is currently building one from scratch. So let's have a look at it.
Okay, so the components that go in this cavity, first we've got modulation coils. So there's this one which sits on the top and also holds the sample, and then has the modulation coil, and that's the matching one that would go at the bottom of the cavity. And then we also have these two, which you can put on the sides, so you can change the setup to match the outside coils. And then the main component inside is the coupling loop, which we have on this moving setup. So this couples to the resonator around your sample. So you put the sample inside, and then we can move the coupling loop to match the resonator and couple up to that. So the way that we move that is using this, which is a differential screw. So this attaches to the top of that, and then by moving the screw up and down, it will move the shaft up and down. Okay, so we've got the full assembly of this bottom part here, and when you can see that when I move this screw, this platform will move up and down. So this is how it will look with the sample inside. So then the resonator should sit just above the coupling.
So that's an overview of the apparatus and a little bit about how it works. Now let's meet Scott, who's going to talk to you about how it was designed in the first place.
My role in the project was to design some of the parts in Autodesk Inventor, and most of these were made in the department by 3D printing. I'm going to take you through some of those designs now. You're now looking at a digital version of the spectrometer, which I designed in Autodesk Inventor. Autodesk Inventor is really useful for designing components in experiments because it allows you to look at all the parts and see if they fit together. And also you can even start to look inside of walls or take away parts you don't want to see, so you can really get to the nitty-gritty in the center of things and make sure everything will work together. So you can now see that we've stripped back the setup to just look at the box and some of the more finer components within it. You can see here that we can take off components and look directly at how we built some of the plastic parts, the 3D printed ones. So here's a small part to hold all of the samples, and then using a lid you can compress it and make sure it doesn't slip down. And testing all these parts is made easier, and it saves time in both printing and experiments later. We can look at each of the parts for containing the coils and shifting up and down the resonators, and we can even highlight specific ones to look in more detail. The program allows us to put precise details into our designs, for example on the modulation coils, which here normally look flat from an outside perspective, but you'll see clearly that there's an angle on them that needed to be added when designing to account for the box's shape. So you can see here we're looking at one of the parts that forms the modulation coils. This originally started life as just a sketch in 2D, which we then extrude into a three-dimensional object. From there, it can be turned into a detailed diagram that shows each of the dimensions, or we could send it directly to be 3D printed. The process of improving our equipment continues to the day, and most recently we've made a new development by changing our design to include a brass differential screw, which Andrew is now going to take you through.
Now here is a naked version of the differential screw. As you can see, it's a 6mm threaded brass bar into a 20mm threaded brass bar. We designed this on Autodesk Inventor, just like we did the other parts. As you can see, it's got slots there machined into the 6mm. That fits into our 3D printed piece, and that turns inside the 20mm threaded bar. And it was made using these two purchased brass threaded rods, a 6mm and a 20mm. But putting those together into something that works was actually quite a feat. So let's go and talk to Aaron in the mechanical workshop, who can talk to us about that.
Right, this is Aaron. Hello. And Aaron is the guy who machined this for us, and it wasn't straightforward. No, fair to say. A bit difficult. So Aaron is going to show you how it was done.
So to make it, it was used with some standard M6 brass rod that I cut to length of, I think it was roughly 50 mil, and then using a cutter mounted in the collet chuck and a dividing head set to 90 degrees, I ran the cutter along and took a few different passes so it didn't take too much depth out at once, reducing the amount of movement that was in the part, which was the main issue. That's why a few of the first ones failed, because the part had moved too much. So eventually I stacked some bits of metal underneath it and really reduced the feed rate, and it helped out a lot to get a good finish and the correct depth of cut.
Brilliant. How long did it take to cut that piece both sides in the end?
Roughly about 20 minutes total cutting time. So it was reasonably quick to do, but getting it correct took a few days.
A few days
of working to getting it going well.
And then you bored out the centre of this one.
Yeah, so on the other part, we mounted it in a lathe and you drilled out the centre and using a tap just ran it the full way down, but it goes quite deep inside, so I had to grind the tap down so it was the same width the whole way so it could get the extra length, because normally it wouldn't have gotten the correct depth, and to buy a tap in would have been quite expensive because it probably would have been a custom tool, so just took it to a bench grinder and ground it down so it fit right.
That's why you need experts in universities to do this kind of job, because nothing's ever standard, is it?
No, definitely not. We do a lot of strange and wacky requests all the time. That's basically the whole job at this point. Nothing's that usual.
Nothing straightforward.
Nothing straightforward.
Well, we appreciate it. So
that's not a problem.
Thanks, Aaron.
You're welcome.
This is an example of the resonators that we use to drive the oscillating magnetic field. Now, the way that we've designed these has undergone quite an evolution in the past few months. Sufficiently interesting to have their own video, so watch out for that, it's coming up. For now, here are Eve and Lucy to show you how we make them.
Okay, so today I'm going to be making a solenoidal resonator. So first thing we needed to do was calculate what capacitance we wanted, given that we have chosen a length of about 1 centimeter. So we calculated from the resonant frequency of an LC circuit and the inductance of a solenoid that we want about 35 picofarads, and I've got two 18 picofarad capacitors, so that'll give me 36, which is about correct. So then I can follow these 1 centimeter guidelines on this, wrap my wire around it, and then solder the capacitors on in a bit.
So here is our resonator, built by Eve. Now, fortunately, we have an expert solderer in our midst at Lancaster University in the electronics workshop, Lucy.
Hello.
And Lucy has soldered a lot of these resonators for us. How many do you reckon you soldered, Lucy?
Oh, it must be at least 50.
A lot. Partly because we keep breaking them, but Lucy's here to save the day, so we're all good. So Lucy is going to show you how to solder one of these resonators.
So now we've gone through all the different parts that make up our spectrometer, and we're going to go through how it works and how we actually use it in practice.
Now, all of our instruments are controlled using the computer and a combination of Python scripts. and we run a series of sweeps. Now what that means is we set this DC supply to a starting level which produces a magnetic field. We know what that magnetic field is because we've calculated the coil constant of our Helmholtz setup. We then set the DC supply to gradually reduce over time whilst we measure the signal from our coupling loop. Now what happens is as this DC supply reduces in power, that changes the magnetic field B0. We have an oscillating magnetic field B1, which is driven by our RF signal generator and inductively coupled electrical resonator. Now at certain points in that magnetic field, that should produce a resonance, which, as we mentioned before, is the electrons in the sample absorbing the energy from that B1 field. Now when that happens, this causes a perturbation in the impedance of the resonator, which means that it's no longer impedance matched to the rest of the circuit. And that means that rather than transferring all of the power from the coupling loop to the resonator, some of it is reflected down this circuit, down through our amplifier chain into the mixer. And that's how we get the DC signal, which we interpret as the signal using the lock-in amplifier. And that's proportional to the absorption of the signal by the electrons in our sample.
So a key component in all of this is the lock-in amplifier. It's what we use to take the measurement, but also to process the data. And so next up is Ed, who's going to tell you what a lock-in amplifier is and how it works.
Okay, so as Andrew told you earlier, we have these two branches of our circuit, both of which can carry the RF signal. One going to the experiment, which is modulated, and one going just round to the other side of the mixer, which is not modulated. When these then meet at the mixer down here, the two frequencies combine, and as a result, what you get out of the mixer on the output channel is a signal that is just oscillating at the modulation frequency. So what we're interested in is the amplitude of that signal at the modulation frequency. And how do we detect that? Well, we use what's called a lock-in amplifier. So lock-in amplifiers are pieces of equipment designed for measuring signals at specific frequencies. So this is the lock-in amplifier I've got in my kit. So I'm using a Zurich Instruments UHF. And the way that they work is that ultimately they are, to a first approximation, also mixers. So they will multiply your measurement signal with your reference. So on this one, the measurement signal is coming out of the mixer, and the reference is coming out of the waveform generator that's driving the modulation, which is then input into the lock-in here. So lock-ins can also do phase-sensitive detection, and the way that they achieve that is when they get their reference channel in, they will split it, and then phase shift one of those by 90 degrees, and then mix both of those independently with the signal input. So it does that by multiplying the two signals together. And again, like the mixer, that means that if you have the same frequency on both of them, that gets modulated down to DC. A lock-in amplifier will then also apply a low-pass filter, and this is what allows us to measure at a specific frequency with a very low noise. And so that is one of the reasons we do modulated measurements like this, is that lock-in amplifiers can measure signals at specific frequencies where the noise at other frequencies can be orders of magnitude larger than the signal of interest. And the clever electronics in a lock-in amplifier allows you to reject all that other noise and only pick out the signal of interest. So that's why a lot of measurements like this will end up using some sort of modulation. So what does the signal look like when you do a measurement like that? Well, we'll cut to a whiteboard and I can talk you through it there. So the response of the system to the experiment, an EPR experiment, depends on the frequency and the magnetic field. So in our experiment, we're generally modulating the magnetic field. Now, the way in which the response depends on the magnetic field will generally be some sort of peak, so like a Lorentzian or a Gaussian. So if on the y-axis here we have some sort of signal intensity I, and on the x-axis we have the magnetic field B, the response of the system will be some peak like that. So in our experiment, we are modulating the magnetic field, which means so if we're applying some oscillating signal, say like this, which has some amplitude like that, and then we, as a result, measure some oscillating response back to that according to its sort of position on this curve here. So we end up with a response that looks like that. Or, sorry, I'm a physicist. I didn't do that for my drawing skills. Okay, like this. So this is why we then, of course, we get an oscillating signal back. Now, the end result of this is that actually we're not measuring this peak shape directly. Instead, what we're measuring is the gradient. If you imagine, as this oscillating section here moves across this graph as the center point of it is varied, the slope of the peak changes and therefore the amplitude of this oscillation changes. So then what you end up measuring as a result of that is something that looks like this. Essentially, just the first derivative, like so. So this is the line shape you would expect to see on the output of the lock-in amplifier.
Alright, so that is all of the theory done. Now Eve and I are going to show you how we use the kit to take a measurement.
Okay, so the first thing that we need to do when taking a measurement is we need to critically couple the resonator to the coupling loop using the setup that we showed you earlier. And the way that we do this is we use a VNA, which is a vector network analyzer. So we're going to show you how to do that now.
So on the screen, you can there see the curve, which is a frequency sweep being done by the VNA. It's sweeping from a higher frequency down to a lower frequency with a width of about 750 kilohertz. And as Eve is turning our differential screw, she's bringing the coupling loop closer to the resonator. And what's happening is more of the power that the VNA is putting out is being absorbed into that resonator, which is essentially an LC circuit, an inductor capacitor circuit with a resonant frequency. So as you can see, the peak is getting sharper because the VNA is measuring the reflected component. So it's measuring the power coming back from the resonator. And the more that gets absorbed into that LC circuit, the less comes back down the coaxial back to the VNA. And as you can see, it's a little bit more difficult to couple this than you might imagine. So as Eve is turning the differential there, that's moving the platform up inside. So as you can see, that is now nicely critically coupled. So the scale there is decibels and it's logarithmic. So minus 70 decibels is very close to 100% loss. So all of the power at that particular frequency, which we want, is going directly into the resonator. So once our resonator is critically coupled, the frequency with maximum loss is passed via the Python script to our radio frequency signal generator, which then stimulates a sample at precisely that frequency. The next step is to run our script and allow the measurement to come in, and we can watch a plot of the measurement data in real time. Now, of course, for your benefit in this video, we've sped that up because I'm sure you've got better things to do than spend half an hour watching a graph appear on a screen. So what you're looking at here is a sweep of the magnetic field, and what's happening is our power supply is adjusting the power to our Helmholtz coils, which is changing the intensity of our field B0. And that is starting at 20 microtesla, sweeping down through zero magnetic field, and eventually concluding at minus 20 microtesla. Now the minus here refers to the direction of B0, and that switches on the z-axis. So you can see that a resonance is developing at around 5 microtesla, and that sort of zeros at approximately zero field. So what we expect to see here is a point of rotational symmetry at the origin. And the eagle-eyed among you will notice that that point of symmetry is not in fact at the zero of magnetic field. What's happening is that the magnetic shielding on our experiment isn't perfect, and some of the Earth's magnetic field is leaking through and adjusting our 0 point. So you can see two approximately symmetrical peaks at around 5 and -5 microtesla, which represents the absorption of this particular frequency of signal by the spin ensemble in our sample. And that is what we'd expect to see for this particular molecule. Thank you for watching this video. We really hope you found it useful, especially if you're working with magnetic resonance or electron spin resonance in the lab. If there's something you can take away from this which has helped, that's great.
Or even if you're not, we just hope that you found this video interesting, maybe learned something new. If you want to try and make your own EPR spectrometer at home, please do send us a picture and let us know how that goes.
Yeah, absolutely. And we will be putting out a couple more videos on EPR on the channel, so please keep an eye out for those. And also, why don't you check out some other videos on the channel whilst you're there.
Thanks for watching.